In this unit, we're going to look at two main applications of derivatives: implicit differentiation, where we work with things that aren't actually functions, and also to look at a related topic, the idea of related rates. Just a reminder, if you define a graph based on a function, so y is a function of f of x, y is a function of x rather, then we know there's a formula to generate the tangent line at any point on the graph. So we have some graph, we can generate the tangent line at a point. For example, what function gives the tangent line, or what function is the tangent line, to y equals e to the negative x at x equals 0? As a good pop quiz, try that by yourself for a couple seconds, and then we'll come back to the question. So our function is y equals e to the negative x. That is our function here. And we know the slopes are computed by the derivative. Negative e to the negative x would be the derivative of f of x. So at x equals 0, and we often called this a in our earlier formulations, we'd have the value of the function, which is e to the 0, which is positive 1, and f prime of 0, which is minus e to the 0, which is negative 1. As a quick sketch, we have the exponential decay function coming down like this, and what we've just computed is that the tangent line at x equals 0 will have slope negative 1, and combining our function pieces here, we can generate the linear approximation. L of x is f prime of a minus 1 times x minus a, x minus 0 in this case, plus 1, or more simply minus x plus 1. There we go. And there we go. Minus x plus 1 is in fact what we're looking for in this particular scenario here. Any others that are close? No. These don't all, none of these work out to be the same formula as what we already have up here at the top. So it's always f prime of a, the derivative at the point we're interested in, times x minus the x coordinate that we're interested in, plus whatever the value of the function is at our point. In this case here, e to the negative 0 is simply 1. Our next question is whether we can do the same thing to all the points on a circle. If we can, we certainly can, if we can write our function, or write the circle, in function form. Y is a function of x. Well, we start hitting some problems right away. Some of you might remember the vertical line test. That's a test for whether a graph defines a function or not. And in this particular scenario, we fail the vertical line test because if we draw a vertical line here, we cross the graph at two different points. And what that means is that y cannot be written as a function of x. Again, for any given x value, I get two y values, so I can't say each input gives me just one output back. And what that means is there's no way we can express the circle, this entire graph, in the form y equals f of x. We can, of course, come up with a formula. We notice the radius here is 4, and it's a circle. And at some point, you've likely seen this already, but we can confirm it just with a quick look at the Pythagorean formula here. If I take any point on the circle, what defines it as being on this circle is that its hypotenuse of any triangle like this, the distance from the origin to the circle, is going to be 4 units long. And then the other two sides are going to be x and y long. You might want to think about absolute values, but the key thing with Pythagoras is the sign of x and the sign of y do not matter because we're going to square them anyway. And so we can use Pythagoras to say that this length squared is going to equal the x coordinate squared plus the y coordinate squared. All the points in the circle will satisfy that equation. Next question is whether we can, at least in principle, define a tangent line. So we don't know how to calculate it yet, but does one exist? Well, if we take a look at the point 2 and root 12, just confirming that it's actually on the circle, we have 4 plus 12, which is 16. So x squared plus y squared equals 16. That's good. We are on the circle. So that would be our point there. And the question of whether we can define a tangent line, I think, is pretty clear. We sure can. We can define a line that touches in just one point. Try that again. Oh, that's a bit better. A line that has the same slope as the circle at that point, and there's no real problem with that whatsoever. Okay. So the next step is to think, how can we compute this? We have a formula, but it's not a function. We have x squared plus y squared equals something, and that's not something we can just differentiate like we have been up until now. But we should be able to do something to find a slope because, well, every point we imagine on here will have some kind of slope associated with it. The solution to our problem of how to compute those slopes is to use a technique called implicit differentiation. And the idea is that you're going to differentiate a relationship, so a relation is sometimes what it's called instead of a function, and because the graph is defined implicitly, not as y equals, but as some combination of x and y satisfying an equation, we can start with this and compute slopes. Now, how is this going to work? We have our relation, and our step is going to be to differentiate both sides with respect to x, or if you like, take d dx. Again, d dx is a verb. It says take the derivative of, so we'll just slide that in here. As long as we do everything to both sides, we should get the same value of rate of change. And when we do that, turns out this right-hand side is actually pretty easy. It's just 0. The more interesting side is over here. What we're imagining is that locally, y can be thought of or can be treated as a function of x. And again, we think of our circle. If I look in some region around a point, this range here, we can define a single function. If I look down here, I could define a different function. And in both of those cases, though, if I just look at them separately and locally, we can think of y changing with x. As x increases, y decreases along this part of the curve. If I was over here, then as x increased, y would increase. So there's a relationship that we can think of as a function. Symbolically, the important thing is going to be x's versus y's. I'm going to use more detail than we usually would in this particular scenario, and I'll explain how it goes in a second. So, the derivative with respect to x of x squared is 2x, and if we wanted to, we could certainly follow up by taking the derivative of x, the inside function, using the chain rule. If we thought that would be helpful, we could do it. In particular, if we think of anything squared and we take the derivative with respect to x, we bring the 2 down front, we get the same thing to the power 1. I'm going to leave that off because it looks like a prime. I don't want to confuse things. And then we would take the derivative with respect to x of the inside function, which is here y. So we can treat everything exactly the same, x's and y's, until we recognize that some of these terms can be simplified. The rate of change of x with respect to x is just 1. In fact, that's why we so rarely write it. It would just turn out to be a 1 multiplier, and it's going to evaporate, it's going to disappear. What will not disappear is the rate of change of y with respect to x. These are two totally different variables. Y changes, y is a height, x is a left to right value in this diagram. Y changes, and it'll change in some unpredictable way with respect to x. So we'd have to leave it as dy dx. Dx dx, just one. Dy dx, well, it's actually the slope we're looking for. And an alternate way to write this out in symbols, of course, is to put y prime. There's no difference between those two. I personally like dy dx just because y prime can sometimes get lost with other y's, but whichever one works for you is fine for us. Okay, what was our goal? Find the slopes of tangent lines for points on the circle. Well, y prime dy dx is exactly what we're looking for then. It's the slopes of sum of y versus x, the ratio of y versus x, for some local region around a point here. I'll go back to that first equation. We're going to bring the 2x over. It becomes negative 2x. And then, last but not least, we can solve for dy dx, which will be minus 2x over 2y, or more simply, negative x over y. That would be the slope of tangents at any point on the circle. Okay, let's put that into action. Let's find the slope at the point 2 root 12. So right here, we just found that dy dx was equal to negative x over y. There's our x, there's our y, and so we get negative 2 over root 12, and with a bit of calculator work, 2 divided by root 12, we get approximately minus 0.577. There we go. Okay. Does that make any sense? Well, let's just draw a slope of minus 0.5, which would be, that's about halfway in that particular cell. So half would be to there, then there. And like so. That would be a slope of negative 0.5, and it matches the graph beautifully. So this value of the slope, being just very, very close to negative 0.5, matches the shape of the circle graph perfectly. And just one note before we go on to other examples, it's worth noting that when we found the slope this way, our formula ended up being negative x over y. So what we had extra here is that the slope can depend on, in this case it does depend on, both x and y on the graph. Okay, so that might not seem like much, but if we think about where we started, it actually could not be any other way. If we were drawing circles, and we ask what's the slope at the x-coordinate 2 root 12, well, we found the slope was around negative 0.57. Let's call it 5/8 rounded. However, if we went to the symmetric point down here, 2 negative root 12, we would have to get a different slope. The slope has to be negative, the other slope has to be positive, and if we use the formula up here, we would get a slope there of positive 0.58. So with that comparison, it becomes obvious that we need, if we have a relation that we're starting with, we need our derivative formula to have potentially both x's and y's in it, so we can tell points with the same x-coordinate only apart from one another.